it's not right. No, it's it's not right to fight about it when you have gone through so many things I could only dream of. No, it's not right to go on about useless things that only tear us apart. No, it's not right. No, it's not fair. No, it's not right. No, it's not
Welcome everyone to Science on Tap. I'm Jen. Thank you all for coming out on this cold winter evening and braving the traffic like I did. Super excited for a new year and to talk more about science. Science on Tap is a monthly educational program. We bring curiosity together with the community to have conversations. Big shout out to our most excellent partners, Radio Artifact and Urban Artifact, for providing this space. And with that, I'm going to introduce our speaker, Wes, to talk about science fiction versus science. I hope you have Planet B options for us because we need one.
Thank you so much, Jen. So thank you for coming out. Like Jen said, I know the traffic was pretty terrible tonight, and so thank you for struggling through it. My name is Dr. Wes Ryle. I'm the astronomer at the Cincinnati Observatory, and I'll talk a little bit about the observatory towards the end of the talk. If you haven't been over there, then I'm definitely going to be begging you to come up to the observatory because it's such an awesome place to check out if you have an interest in science and science education. The topic that I'm talking about tonight is science fiction versus science fact, which is a fun topic just because we get to do a little bit of nostalgia, especially if you're a science fiction movie fan. And we kind of get to make fun of some of these science fiction movies as well. Spoiler alert, if you haven't seen Star Wars or some of the Star Trek movies, there might be a couple of spoilers here, but quite frankly, if you haven't seen Star Wars, then I'm sorry for you, and there's really no excuse at this point. So, as a disclaimer, I am definitely a science fiction fan. And so, give me just a second. There we go. So I definitely do like sci-fi. I'm not, even though you might hear that sometimes scientists aren't the best people to watch a science fiction movie with, I can suspend my disbelief and actually enjoy a science fiction movie just like the rest of y'all, okay? That doesn't mean that I'm not analyzing different pieces of science fiction and kind of saying, oh, they kind of messed that up a little bit. But if the plot is good, if the characters are good, that's fine. That said, tonight's talk is really about some of the things that they get right and some of the things that they get wrong. And chances are, when you've been watching some sci-fi movies, hopefully you have been able to tell a little bit about, I don't know if that's really that realistic versus something that's like, wow, they actually did their research there. They actually figured out how this would actually work, say, on the surface of Mars or whatever it might be. And so I grew up reading Asimov. One of my favorite books is Ender's Game. Do we have any folks, fans of Asimov out there? Yes, no, maybe? Okay. Ender's Game? Star Trek or Star Wars? Okay. Yes, as in yes to both. That's fine. Yeah, I'm not definitely not somebody who prefers one over the other. I definitely enjoy them both. I also enjoy space-based and science fiction-based video games. And so if there's anybody who plays video games out there, Mass Effect was a wonderful series. Halo was a wonderful series. Starfield, not so much, if anybody played Starfield out there. And No Man's Sky is a really great game. It started out pretty bad, but actually turned into a really, really great game. And so I'm a consumer of science fiction. But tonight I'm going to be a little picky. I'm going to actually take up a fight with some of the sci-fi that's out there. And the reason is that there is a lot of bad sci-fi out there. And maybe after tonight you'll see some of these movies. I'm not necessarily recommending that you go see them for enjoyment, besides maybe just laughter, right? In order to kind of make fun of them, because some of them are just really, really, truly bad. And so as examples of bad sci-fi, sorry, lost some of my images. As examples of bad sci-fi, yeah, we hit a tachyon field. That's definitely what happened here. That's funny that they're showing up on the side and not on the main screen. I'm going to try restarting the presentation just real quick. Please don't make fun of my very messy desktop. I think I heard some groans when you saw that desktop. All right, it looks like it's behaving now. Okay, so bad sci-fi in my book. Armageddon. It's an action movie, and there's lots of star power on it, but there's definitely some bad sci-fi in there. Did anybody see Apollo 18? It was a relatively recent movie. Don't bother. It was about, of course, the 18th Apollo mission that was kept secret because of the evil discoveries that they found on the moon. 2012, disaster movie, of course, all having to do with the Mayan calendar, which, if you remember, back in 2012, there was all the hype about the end of the Mayan calendar and how that corresponded to the end of the world. And then my contender for possibly the worst sci-fi movie, The Core. Is there anybody who's experienced The Core out there? Okay, this is one that might be worthwhile watching just because it is so absurd, and we'll have some clips from it in just a little bit. And also in the very recent category, this was just a couple of years ago, Moonfall. Anybody watch Moonfall? No, it's just as bad as it sounds. The moon unexplainably falls towards the earth. And it is a very chaotic scene, but that's possibly a new contender for the worst sci-fi movie in my book. But again, we'll show some clips for all of these. I'm definitely not the first person to critique astronomy or science that's out there in the media. If you've ever heard of Dr. Phil Plait, he refers to himself as the bad astronomer, and there's actually a really good book that he put out called Bad Astronomy. And he's even got his own website where he talks about a lot of science that's in pop culture and what they get right and what they get wrong. And so if you kind of like what you see tonight, it's worthwhile to check him out too. So let's get right into it. There's lots of different things that we could be picky about as far as sci-fi goes. We're going to start out with sound in space. And I think at this point, most people realize that when you're depicting an action scene out in space, there's a problem with having an audio component to that, right? I am somebody who is watching a movie for the thrill of it, and so I'm okay with there being sound in the action sequences. But of course, actual sound needs a medium to travel through, and out there in space, It's so thin, it's essentially a vacuum. There's not any material for the sound waves to actually transmit through. Now, if you were watching a science fiction movie and it was just completely silent for all the battle scenes, that would be pretty boring. I do admit that. And so they do add something. And so here's a very classic example of sound in space from Star Wars. So, of course, you can hear the whizzing of the spacecraft as they go down the trench.
You're all clear, kid. Now let's blow this thing and go home.
You can hear the torpedoes fire.
Stand by. Stand by.
And you can hear the Death Star explode. Again, if that was a silent scene, that would have been not nearly as dramatic. Okay, so I'm not necessarily opposed to having sound in some space scenes. But one of the things that I want to show is that in some cases, it can amplify the drama of the scene if you do show how there is no sound in space, if you make the switch to show that space really would be silent. And so this is from the reboot of Star Trek, and this is one of the first scenes early in the movie where one of the starships is being attacked, and we'll see a very traumatic scene where someone gets pulled outside of the ship, and just pay attention to the sound and how it makes the scene that much more dramatic. So it feels scary, right? Because you have all that dramatic sound inside the ship, and then the moment that the camera follows the person out of the ship, it's completely silent, and so much more dramatic. Did that feel more dramatic? Yeah. The same movie actually does another scene a little bit later that actually switches kind of around the other way, where it goes from silence to sound, and it builds up the drama in kind of the opposite effect. And so this is a scene from Star Trek where they're leaping out of the spacecraft in some suits and they're plummeting down to the surface, but they start out in space, outside the atmosphere, and it's silent, and then as they get closer down, you can eventually start to hear the air whizzing by.
Awesome. 3, 2, 1. Remember, the Enterprise won't be able to beam you back until you turn off that drill. Good luck.
So here's the silent portion. And they add the fact that you can only hear the breath of the person.
Away team is entering the atmosphere, sir. 20,000 meters.
So they've started to enter the atmosphere. And you hear the sound building up. Again, just kind of adds to the drama of the scene. Again, there's issues there because typically if you're an object that's outside the atmosphere, entering the atmosphere at a very, very high speed, what would happen? Yeah, and so friction with the atmosphere would build up rather quickly, and these brave soldiers, brave space crew would have been kind of incinerated as they come down. But again, we'll ignore that fact. Now, another thing besides sound in space that sometimes goes awry in sci-fi movies, and it almost kind of has to, is how we travel in space. And so I'm going to contrast two scenes from Armageddon, or one scene from Armageddon and one scene from Battlestar Galactica, kind of the reboot of Battlestar Galactica. Any fans out there of the reboot of Battlestar Galactica? Yeah, it went downhill, but the first season, I think, was some of the best sci-fi that was out there. And so this is a scene from Armageddon where, of course, they're in pursuit of the comet that's coming towards the Earth. Again, spoiler alert. Just so that they can put nukes on it, because nukes always solve all your problems. But what I want to point out is how the space shuttles here fly. Pay attention to how they fly.
Everybody hang on. This could
So do you see how they're banking? Yeah. So in those scenes, those external scenes where they're showing the spacecraft that, in this case, what was essentially a space shuttle, flying through that debris field, in order to turn right, you see them bank to the right, and in order to turn left, you see them bank to the left. What's the problem there? Right. Why do planes bank? What does that actually do? Yeah, it's all about lift and the aerodynamics, but aerodynamics require air, right? And so if you're a plane flying through an atmosphere, yes, you turn and you bank in order to go wherever you need to go. But if you're in space, there's no air resistance, there's no aerodynamics. Things travel in straight lines when you're out there in space. If you fire your thrusters, it'll change your motion. But if you stop firing your thrusters, you're just always in straight lines. And so it's a very different type of motion. And it's relatively rare to see sci-fi that actually gets that motion right.
Everybody hang on.
But Battlestar Galactica was an example of a show that actually did this pretty well. And so this is a scene where there's a squadron of space fighters coming in, and there's a couple of different maneuvers that they do that kind of shows this concept.
Okay, Boomer, we'll take it from here. You're back way off.
Roger that.
And so notice that this ship is detaching from the rest, and it just fired some little thrusters and puffed up. Here the ships lose power, and you notice that they just continue to drift in whatever direction they were going when they lost power. And so those are two really good examples of how space travel would actually be, right? You do not need to constantly fire your thrusters when you're traveling in space. In fact, every mission that we send out to the moon or out to a distant planet, Jupiter, Mars, Pluto, whatever it might be, it's actually a very small fraction of the time that they're ever firing their rockets, because you give it its initial boost and then you just rely on coasting out to whatever destination you need to go to. You might do some small minor course corrections along the way, but for the most part you're not burning fuel, because fuel is very hard and expensive to get up into space in the first place. You also notice that in that initial scene where the one spacecraft kind of lifted up and away from the rest, there was those little puffs, those little jets that came. That's actually how a lot of spacecraft control their orientation in space, just by doing little puffs of pressurized gas in order to change their orientation or change their, say, altitude or elevation ever so slightly. Burning rockets and burning fuel all the time is not going to work, and banking is definitely not going to work either. I mentioned that I'm a big fan of space-based video games, and of course one of the most fun things about a sci-fi video game is flying your spaceship. Being an astronomer for over 20 years, I still desperately want to fly my own spaceship. And my wife has to hear that all the time when we're watching a sci-fi movie. It's like, man, I really wish I could fly a spaceship. But the funny thing is that almost all space video games, they do use the banking, right? Because it's more intuitive. People kind of get the sense of, if I had a joystick in front of me, you know, if I push it left, the plane's going to go left, and if I push it right, the plane's going to go right. If you had video games that were really like how motion works in space, it would be incredibly frustrating and hard to adapt. And so if we ever do have a situation where people are, I know it sounds absurd, but we're talking about science fiction and science fact here, but flying spaceships kind of on a regular basis, right? We do have a space force right now at this point. Then that motion, that maneuvering is going to be intensely different than using an airplane, and it's going to take a huge amount of adjustment, again, because you're always drifting in straight lines, and any little burst to the engines that you give is going to change your trajectory. Now, moving forward in terms of travel in space, I hear chuckles for Spaceballs. So the other problem that we always encounter in science fiction is the fact that we need to get from point A to point B, and point A and point B are usually different planets or even different stars. And of course, in reality, the distances between planets is huge. The distances between stars is enormous, right? As an example, right, when we sent astronauts to the moon back for the Apollo missions, or coming up with the Artemis missions within the next couple of years, we're going to be sending astronauts back to the moon. Those trips last maybe a week, right? Maybe a little bit more than a week for getting there, getting back, depending on what they actually do. If you want to send a mission to Mars, right, which realistically we could do within the next maybe 20, 30 years, if you want to do that, that's going to take probably at least a minimum of 2 years. And that's because it's going to take months to get there, and the planets are moving on their own orbits, and Earth and Mars take about 2 years to sync up, right, in order to be close to each other. And so a few months out there, you're going to spend maybe a year or more on the surface, and then a few months back. That's a 2-year round trip. Obviously, that's not exciting movie to watch somebody have to wait 2 years to actually get to their destination. Likewise, even a week to the moon, right, isn't necessarily exciting TV. But then on top of that, you have to think about all these sci-fi usually have travel between stars. That is something that we are not anywhere near capable of with any kind of technology that we have today. If you wanted to send a human to the nearest star system, you're talking about probably tens of thousands of years for that journey. Right? To give you a sense of scale, you know, if you had a ball that was about this big to represent the sun, the nearest star to our own, Proxima Centauri, would have to be roughly somewhere down in the Florida Keys. And so it's huge, huge distances. Okay? And so they always have to take shortcuts. And with most movies or TV series, you've got things like warp for Star Trek. You've got hyperdrive for Star Wars. Some people call them jumps. There's all sorts of different terminology. But Spaceballs actually made fun of this concept itself and went with something completely different.
Ludicrous speed! Sir, had you better buckle up? Buckle this! Ludicrous speed! Go!
So there's what you typically see in these kind of jumps with the like stars streaming out.
What have I done? My brains are going into my feet. What the hell was that? Spaceball 1. They've gone to plaid.
And so they're making the joke that they've gone to plaid because whenever you see faster than light travel, right, in sci-fi movies, it's usually either the stars whizzing by or a blue glow like in the Star Wars movies. In this case, they've gone so fast that it turned to plaid. And so it's definitely making fun of this concept in sci-fi movies. And of course, sometimes they refer to it as light speed, but the funny thing is that light speed would even be too slow, right? Because you know, you've heard of the term light year, right? That's the distance that light travels in a year. And so, for example, Proxima Centauri, the nearest star to our own, is a little over 4 light years away. And that means that if you were traveling at the speed of light, it would take you over 4 years to get to that star. And light speed is really, really, really darn fast, but still take you more than 4 years to get there. And so all of these sci-fi concepts about travel between stars, they're talking about speeds that are much in excess of the speed of light. And of course, it's always convenient for the plot how long it actually takes to get from one star to another. Sometimes it takes like 10 seconds, and then other times it's like, oh, it's going to take us a week to get to our destination. Now, the other comparison that I had at a couple slides ago was Spaceballs versus Ender's Game. And so Ender's Game was made into a movie. It was originally a book. But one of the things I really liked about Ender's Game is that the space travel in that book actually applied some real physics, some good physics. And in particular, they did have spacecraft that could achieve speeds near the speed of light. And that's a stretch. We can't do that right now. But maybe sometime in the future we can actually build ships that can go up to close to the speed of light. What's interesting is that Einstein's special relativity suggests that when you travel at speeds close to the speed of light, things get very, very weird, right? The whole reason it's called relativity is that space and time are relative, and different observers can experience different distances, lengths, or even the passage of time. And when the theory of special relativity first came out, there was something called the twin paradox. Well, there's still something called the twin paradox, where it says that if you had, say, twin brothers or twin sisters, and they're both on the Earth, they're both obviously the same age as their twins, and one decides to stay on Earth while the other decides to go on a mission to a distant star, if the person that goes on the mission to the distant star travels at relativistic speeds, at speeds near the speed of light, time will flow differently for them compared to the person that's back on Earth. And depending on how fast they're going and how long they travel, if that individual returned back to Earth, they will have aged differently than the person that stayed on Earth. And in particular, the person who was on the spaceship will be younger when they return than their twin who stayed back on Earth. The flow of time is actually different. And that sounds like sci-fi, but that is absolute science fact. We can't do this with people in spaceships. That would be cool. But we can do it with small subatomic particles, and we actually do this really regularly with small subatomic particles in like atom smashers and particle accelerators. They actually rely on the fact that time flows differently for those tiny little particles than it does for the rest of the lab that's at rest. We even use this for like the GPS system. And so the GPS satellites that might have gotten you here tonight, they rely on special relativity and general relativity and the fact that time flows differently for those spacecraft than it does for us here on Earth in order to have those really accurate locations. And so this is something that's cool, that's real. And then if we ever get to the point where we can actually send spacecraft out at speeds near the speed of light, this is a real consequence that we'd have to deal with. In the book and movie Ender's Game, spoiler alert, one of the ways that they use this is that in the first war with the aliens, there was one individual who figured out the key to defeating the aliens. And they were worried that the aliens were going to return a couple decades later, because the travel was more realistic in these books. And in order to preserve that individual, they just sent him out in a ship at relativistic speeds and had him return to Earth so that he aged slower than the rest of the people back on Earth so that they could preserve him and his knowledge about how to defeat the aliens. And so that's a kind of cool little plot device that they included in the book that's actually based in real science. All right, so this is a common occurrence in sci-fi movies. Whenever you want to get away from the bad guys, you need to escape through the asteroid belt, right? And so a classic example is Empire Strikes Back. And so quick clip from that.
Joey sent you 7-1.
What are you doing? We're not actually going into an asteroid field.
They'd be crazy to follow us, wouldn't they?
Pay close attention to how the asteroids are moving and how many they are.
I have to do this to impress me.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
All right. So again, a very dramatic scene, and again, I love the fact that it's a way to increase the drama and have a chase scene that's really, really effective in space. But this does give people the impression of what, say, the asteroid belt in the solar system is like. And truth be told, the asteroid belt in the solar system is nothing like this. If you think about it, there's been a lot of different missions that we have sent out through the asteroid belt. We send spacecraft to Jupiter, we've sent spacecraft to Saturn, we've sent spacecraft to asteroids in the asteroid belt. We've sent spacecraft to Pluto, and they've passed by Uranus and Neptune. When the first spacecraft was sent through the asteroid belt, they actually did have some concern on whether it would make it or not, but it wasn't because of a big giant asteroid risking collision with it, but they didn't know how many tiny little fine particles there were in the asteroid belt. Because even the smallest, tiniest little particle moving at these big speeds that the spacecraft and the asteroids themselves would be moving at would be enough to really severely damage the spacecraft. And so they didn't know how many fine particles there were. It was a risk, but they sent the spacecraft through. It took measurements of how crowded the asteroid belt, how much debris there was, and it was smooth sailing, right? And we have sent numerous spacecraft through the asteroid belt since. The somewhat disappointing fact is that in reality, if you were in the asteroid belt and you plopped yourself down on any given asteroid and looked out into space, you wouldn't even see another asteroid from that location. There are millions of asteroids out there, right? But they occupy a very large amount of space spread out in that ring around the solar system. And so even though there's millions of them out there, you could stand on one and not see another because the distances are so huge. Add on top of that, that asteroids are very, very tiny, and so they're going to be very small, very hard to see if they're at any kind of distance away. It's safe to travel through the asteroid belt now. We do it all the time, and in fact, every time we send a spacecraft through the asteroid belt, we actually intentionally make it pass very close to an asteroid because it's bonus science, right? If you're sending a spacecraft to Jupiter, why not have the spacecraft pass by up close an asteroid along the way, plan that encounter, take measurements and data and pictures along the way? And so almost every spacecraft that passes through the asteroid belt now does an up-close picture of an asteroid as it goes. Make sense? All right. Now, speaking of asteroids, of course, a lot of disaster movies have to do with the fact that Earth can be hit by asteroids or comets. And in fact, we know pretty definitively at this point that the Earth has been hit in the past and caused massive global damage. Like, for example, the impact that was responsible for wiping out the dinosaurs, but also more than 50% of the species on the Earth, right? Not just the dinosaurs. And there, of course, have been meteors that come down through the atmosphere quite regularly. If you remember, back just a few months ago, there was one that was visible from here in downtown Cincinnati. Did anybody see that or hear about that? It was a night where there was a concert at the Red Stadium. There was a Green Day concert at the Red Stadium, and there was a Bengals game going on at the same time. And the meteor came down over Kentucky. And so everybody who was sitting in the Red Stadium and on a certain side of the Bengals Stadium looking south saw this bright meteor come down through the sky. Very, very bright. Hundreds of reported sightings, of course, from here, but then all around the region. This happens all the time nowadays. These get reported because we have cameras everywhere, right? Think about all the doorbell cameras and stuff like that we have, the dash cams. So meteors get reported a lot more frequently now just because we have so much more recording equipment than we used to have. You might have even heard about the one that came down over Russia and exploded up in the atmosphere and ended up shattering lots of windows in a large city. And so impacts do happen. But with this in particular, Armageddon overdid it. right? Nature is scary enough. They didn't need to exaggerate as much as they did. And so let me show you a clip from Armageddon.
What hit us? Small asteroid fragments. This morning. How big were those?
Those were nothing. The size of basketballs and Volkswagens.
This new one you're tracking, how big?
It's the size of Texas, Mr. President. It's what we call a global killer. The end of mankind. Half the world being incinerated by the heat blast.
So audio might have been a little bit muffled there, but at the very beginning, there had been some small impacts that, of course, had happened directly at New York City. And somebody asked, a concerned general asked, how big were those? And he said they were the size of basketballs and Volkswagens. At least that was decently accurate, right? Something maybe the size of a basketball or a Volkswagen could survive the trip down through the atmosphere without completely burning up and maybe actually impact the surface. But then he says, well, how big is the one that's coming, right? And he says, it's the size of Texas. Yes, that would be cause for concern. But that is overdoing it. Literally, if you had an asteroid the size of Texas impact the Earth, you're not just worried about global mass extinction. You're worried about liquefying the surface of the Earth. You're worried about knocking the Earth off of its axis. You're worried about changing the orbit of the Earth at that point. You don't need something the size of Texas to really create a threat. And to get that point across, this is a simulation that shows a hypothetical impact of an object that's about 6 miles wide. And it impacts just off the coast of New York. Again, I don't know why people are picking on New York here. But the asteroid is 6 miles wide, right? That's similar in size to what the asteroid that is believed to have wiped out the dinosaurs and 50% of the species on the Earth. That's similar to the size that it was believed to have, okay? 6 miles wide is obviously a lot smaller than Texas, right? If you've ever had to drive across western Texas, you know that 6 miles wide is a whole heck of a lot smaller than Texas. Now, even though that's a whole heck of a lot smaller, and that is tiny compared to the Earth itself, the speeds that these things are moving at are so high, right? Both the Earth and the asteroid itself are moving at such extreme speeds, many dozens of miles per second, not per hour, per second, that the energy associated with those kind of impacts is huge. And so this video, I cut it up a little bit. This view obviously shows the asteroid looking really big, but that's because the camera is right next to the asteroid and the Earth is way off in the distance. Now, more realistically, do you see that tiny little point of light? That's the asteroid as it was passing down through the atmosphere. And then that bright glow right there is from the actual impact. And this is a pretty decent simulation of what that kind of impact would do, and a pretty decent simulation of what that impact would look like for the dinosaur killer that impacted down in what is now the Yucatan Peninsula. You see a couple of different shock waves here. There's one shock wave that's a wind blast. There's another shock wave that's a heat blast. And you notice this one impacted off the coast of New York, but it's already incinerated Cincinnati here, right? And if I bring the video back just a little bit, right before the explosion, there, right? So that little dot is the glow of that asteroid passing down through the atmosphere before it hits the surface. 6 miles compared to the size of the Earth. It's small, it's insignificant, but it does global damage. Again, if you went the size of Texas, you've got a lot more problems than wiping out 50% of the species. That's probably wiping Earth as a complete clean slate at that point. All right. Now, I promised that I view the core as the worst offender. I'm sure there's probably worse sci-fi movies out there, but at least in my experience, this one was pretty bad. In the core, of course, the Earth's core, for some unknown reason, stops spinning. And there is at least some good science there, in the sense that Earth's core does have a rotation associated with it. And the rotation of Earth's core and the fact that Earth's core is partially molten is very important for protecting life here on Earth. So a rotating molten core made out of things like iron, like our core is, actually generates a magnetic field that surrounds the Earth. And our magnetic field is very important for deflecting harmful particles that come from the sun. This past year, it's been multiple times where we've gotten to experience these violent solar storms that have come and produced aurora all the way down here in the Cincinnati area. That's been something that's very special that's happened. And we're lucky that Earth's magnetic field protects us from that the majority of the time, right? Unless it's an extremely violent storm, an extremely strong storm, where we can actually see those particles leaking into the atmosphere down deeper, further south. Most of the time it just happens up at the poles. And so Earth's core, very important. The fact that it's molten and spinning, very important. The fact that it produces a magnetic field, very important. That's about all the core gets right. It goes very much wrong after that. This next scene kind of describes what I was just describing to you, but I can never watch this scene with a straight face. And so see how you interpret it.
What's the timeline here? As the EM field becomes more and more unstable, we'll start seeing isolated incidents. One plane will fall from the sky, and then two, and then in a few months, everything electronic will be fried.
Static discharges in the atmosphere will create superstorms with hundreds of lightning strikes per square mile.
After that, it gets bad.
The Earth's EM field shields us from the solar winds, which are a lethal blend of radioactive particles and microwaves. When that shield collapses, microwave radiation will literally cook our planet.
Dr. Zimsky. This is the sun. This is the Earth without the EM field. Would you?
Very concerned looks from the important gentleman there. So again, there's some good science in there, right? He mentions that it's responsible for the magnetic field. The magnetic field protects us from particles coming from the sun. That is absolutely true. But he mentions it protects us from particles coming from the sun and microwaves, which the sun doesn't actually emit a whole heck of a lot of microwaves. It emits visible light, the light that we can see. It emits infrared light. We feel that as the sun's heat. It emits ultraviolet light. We get sunburned by that. But microwaves isn't a huge contributor to the output of the sun. And I don't know why, well, I do probably know why. Somebody picked up on microwaves and insisted upon that being the harmful thing, because we think about microwave ovens and how they cook things, right? And so in this movie, for drama, they wanted to be able to cook things, and so they chose to highlight the microwaves, when in reality, microwaves are the least of your issues. They even go so far as to have these concentrated white microwaves, of course, attack prominent monuments in cities. And so here's a view of one of these holes in the magnetic field letting the evil microwaves through. It's a microwave, it's boiling water, right? That makes sense, sure. Rolling up the window will help. So, of course, the bridge snaps and disaster, and then it takes out half of San Francisco and all that kind of stuff. Now, first off, microwaves aren't coming from the sun. They're not in any kind of concentrated form like that. The other problem is that microwaves, yes, your microwave oven does use microwaves, absolutely. But it uses one very specific type of microwave. Right? Whenever you're talking about light, whenever you're talking about different forms of energy, those have frequency or a wavelength associated with them. And in particular, with a microwave oven, it's using a specific type of microwaves that gets water molecules excited. It makes them bounce around, which causes them to heat up. And so that's why when you put something that has a lot of moisture, a lot of water in it, it heats up rather efficiently in a microwave. But if you put something that's very dry in there, it's not nearly as efficient. Go home and try to microwave a saltine cracker. I promise it's not going to heat up all that much because it's only exciting the water, okay? And it's a very specific microwave. There is a range of microwave frequencies, wavelengths, energies. In fact, not to scare you, but this uses microwave frequencies. Your Wi-Fi uses microwave frequencies. If you've still got a cordless phone at home, it uses microwave frequencies. Those are not the frequencies that get water excited and therefore don't bake anything or fry anything. And so microwaves are abundant. We are inundated in them right now, but it's only the very specific type of microwave that's used in a microwave oven that's going to do any kind of damage like you see in that picture there. And of course, it's all moot because the sun doesn't emit that much microwaves anyway. The movie even gets worse from there because this is just the beginning. After this, they have to go down to the core of the Earth in order to get it spinning again, right? Because that's going to be easy to do. It's hopefully obviously, harder to travel into the Earth than it is to travel out in space, right? But they, of course, miraculously do that without getting crushed. And what do you think they do in order to get the Earth's core spinning again? Yep, they use nukes. Nukes will solve all your problems. Yeah. Mm-hmm. And then this was, again, a more recent movie. This was definitely not on my list to watch, but I was watching my parents' cat, and so I was just over at their house, home alone, and it just happened to be on, and I thought, why not? Give it a try. And so this one was called Moonfall. Just came out a couple of years ago, and it might be a new contender for my worst sci-fi movie. Let's watch a scene from the trailer. Don't ever let the moon sneak up on you.
Jimmy, hold my hand.
Come on, let's go. Let's go.
Jimmy, hang on. Don't let go.
So the idea there is that for reasons that I won't spoil the movie for you, for reasons that will remain unknown, the moon has become much, much closer to the Earth. And as a result, it's obviously causing chaos on the Earth. And here in this scene, as the moon rises and becomes directly over those folks, you encounter the fact that the moon's gravity is a lot stronger because it's so much closer to the Earth that they're actually physically getting pulled up, along with the air, the atmosphere getting pulled up towards the moon. So yes, technically, I mean, if the moon was closer, the gravitational pull would definitely be bigger. But there's obviously some other problems with that. And what's interesting is that this does happen in our solar system, has happened in our solar system, where moons have gotten too close to their planets. And so there's something called the Roche limit for any given planet, technically any large, massive body, where if a smaller body gets too close to the larger body, say a moon gets too close to a planet, or maybe an asteroid gets too close to a planet, you end up with tidal forces stretching the moon and actually causing the moon to disintegrate. Now, I use the word tidal in there, just like with our moon. There's tidal forces. And tidal forces just mean that for our moon, one side is getting tugged, the side that's closer to the Earth is getting tugged a little bit more, the side that's farther away is getting tugged a little bit less, and that causes the moon to get stretched. That's what a tidal force is. It's created by a difference in force on each side of the body. If the moon gets too close to the planet, those tidal forces become strong enough to completely shred the moon and cause it to disintegrate. And I said that this has happened before in our solar system because we have evidence of planets that have debris all around them. What's an example of a planet that's just completely surrounded by debris? Saturn, right? And so one of the leading theories, and not completely proven, but one of the leading theories for formation of the rings of Saturn is that you might have had a moon of Saturn drift too close to the planet, become disrupted, and basically become shredded, become those rings. And most of the moons of Saturn are made up of icy material, and the rings of Saturn are made up of icy material. And so this could be an example. I mean, this definitely does happen in our solar system. And there's actually an example in our solar system of a moon that will do this at some point in the future. And so this is a close-up picture of Triton, which is a very large moon of Neptune. And so Neptune's there in the background, Triton's in the foreground. This is a photoshopped image so that they're just right next to each other. But Triton is a very, very large moon, and it orbits Neptune in the opposite direction that Neptune rotates. That's called a retrograde orbit. And what's funny is that when you have that situation, the tidal forces on the moon will gradually make the moon spiral inward closer and closer and closer to the planet until eventually it will get too close to Neptune and will become tidally disrupted. Now, it's a gradual process. It's going to take millions, possibly even billions of years. I forget the exact number. But at some point in the future, Neptune is likely to have this big, beautiful ring system when Triton gets disrupted. Also, the fact that Triton has this orbit that's opposite the rotation of Neptune is a pretty clear indicator that Triton didn't form with Neptune. It actually was captured by Neptune. And so this is likely, it's actually something similar to Pluto. It's like as if Pluto kind of drifted too close to Neptune and got captured by its gravity. And so again, there's some cool science there in moonfall, but truth be told, if the moon was actually as close as they showed in that scene, it would have been completely tidally disrupted at that point, in addition to causing severe damage to the Earth at that point as well. Now, also noted with that, you might have heard this, our moon is orbiting in the same direction as Earth rotates. That's called a prograde orbit. And that actually, the tidal forces in that case, cause the moon to gradually get further and further away from the Earth. And so our moon is drifting away from us by just a few centimeters per year. And the crazy thing is that we can measure that really, really accurately. For example, the Apollo astronauts literally left mirrors on the surface of the moon that we can bounce laser signals off of in order to get very, very accurate distances in order to see how that drift happens over time. You might have also heard that that means that at some point in the future we won't have total solar eclipses. So like back in April we had the beautiful total solar eclipse. When the moon gets far enough away, it will no longer be able to completely cover up the sun. And so total solar eclipses will not happen at some point in the distant future. Now to kind of round off the talk, mention things where science fiction has actually become science fact. Right? And so kind of done criticizing the movies and the books at this point, and now kind of complimenting them in the sense of what we've actually accomplished that we thought was just purely science fiction in the past, but is really true nowadays. And of course, if you are a big fan of Star Trek, they always whip out their tricorder in order to do different readings of the environment, to do different medical readings, whatever it might be. This is actually really outdated because that's like a little It's not even an iPhone, I don't think, there. But notice the similarities, right? I mean, there obviously are huge similarities, and you have access to more information on your phone, right, than anyone back 50 years ago could have possibly imagined. And it's not that far off from the idea that you can do readings for your health in your body, right? Because at this point, we're wearing smartwatches and things like that are measuring our heartbeat, that are monitoring our sleep, all that kind of stuff that the tricorder was doing for Star Trek in the past. Your phone can even do things, depending on the models, some of them can read the pressure of the air, how far you are, how high you are in altitude, how much you've accelerated, right? If you come to a sudden stop, for example, there's some phones that if you're in a car wreck, it detects it, right, and does an automatic notification. And so all the different things that they were imagining a tricorder doing is stuff that it really can do today. The internet was genuinely sci-fi, even as early as authors like H.G. Wells, suggesting that in the future there would be a repository of information that was available to everyone, right? Not even just the elite, but to literally everyone. And for better or worse, that is what we have today, right? Whether it's accurate information or not, that is definitely something that's true. Robots. I mentioned I was a big fan of Isaac Asimov, and he has a lot of books that were devoted to robots, and in particular, robots that were attempting to be as human as possible. And that is something that we're definitely trying to move towards today. This is even an older model, still a little bit creepy. Sometimes people, if you've ever heard of the uncanny valley, right, where thing looks almost human but not quite human, and that's just really, really, really creepy. We're still trying to overcome that with a lot of robots. But we're getting to the point where, I mean, literally, if you wanted to order a house assistant robot, they are out there. They are actually out there. There was a big expo just within the last month that was showing some of the latest developments in robot technology. This one is one that, as a kid, I always thought was just vitally important, and thought, well, maybe if we had a world where people could just actually talk to each other, things would be actually so much better. And we're there, right? I mean, I have no idea how to speak German, but here on my phone I can do, I think The Core is the worst movie in history. Oops, let me turn it up. So I don't speak German.
Ich glaube, The Core ist der schlechteste Film der Geschichte.
Anybody speak German out there? Yeah. So I don't know whether it's actually doing a good job or not, but I imagine it's doing a lot better job than I could possibly do. And I don't know if any of you all out there have been on trips to non-English speaking countries lately and maybe even tried that out. But look, I mean, it's so fast. That's the thing that's really, really improved. And I think we're getting to the point very quickly where we could literally just have an earpiece, right? And it's translating in real time so that we can actually talk to each other. And of course, this was something that was available on Star Trek for talking between the different alien races. Cloning, right? And so Jurassic Park fans out there, either the book or the movies, that all relies on the idea of genetic cloning. And of course, eventually that came true with, do you remember what the name of the sheep is? Dolly, yeah. And so Dolly was one of the first examples of successful cloning. And again, this is not in the realm of science fiction anymore whatsoever, because there are lots of companies out there that will literally clone your favorite pet. Has anybody in here done that? Yeah? Yeah. So this is something that you can do, and this is something that people do very, very regularly. And so if they've had a beloved pet that has passed away, they will save a sample from that pet, and it will be replicated, cloned. It will be implanted into a surrogate mother, right, and then born, and you've got an exact copy of your former pet, if you've got the money, right? And so if you've got a pet that's getting kind of old, I've got a cat that's 18 years old. No offense, I love the cat, but I think I don't want a clone of him. If he's listening, then I'm sorry. And then today, we are still developing science fiction, looking forward to the future, and it's always interesting to think of what of this science fiction is actually going to become true. Jen and I were talking beforehand about the idea of transporters, right? You see transporters, especially in Star Trek, and that would have come in really handy to avoid the traffic today, and obviously would completely revolutionize the world. Likewise, in Star Trek, there's just the replicators, right? Just to being able to create food on command, right? Those kind of technologies, at least as of today, have no basis in reality. But it would be really, really cool if they did. But there are some things that are possibly within grasp. And so in the upper left there's a picture of a little mining base on an asteroid. And this is something that's definitely within our capabilities at this point. If you go back a decade or more, NASA actually had plans to redirect an asteroid, where they were basically going to go and capture the asteroid and bring it to a near-Earth orbit so that it could have possibly a base on it. You could explore what kind of precious metals might be on the asteroid and actually mine it for profit. And this is something we do have the technology to be able to do, which is both exciting and also very, very scary because, again, if you want the plot for a science fiction movie, if you can redirect an asteroid to bring it in to mine it, you can also redirect an asteroid to bring it in and aim at your enemies, right? And maybe even cover it up so that you don't know that it was sent there intentionally. And so that's some scary stuff. But we also have plans with the Artemis missions to build a moon colony, definitely within the next 10 to 15 years. And the same is true for China, right? There's a little bit of a space race going again in terms of getting back to the moon and establishing bases on the moon. Down there at the bottom, if you've ever seen the movie Artificial Intelligence, it was actually a pretty decent movie. But obviously AI has become a huge topic in the last couple of years. And while it's not anywhere near kind of what we usually think about as true artificial intelligence, things are progressing very, very, very rapidly, and enough to get a lot of big minds and big voices kind of concerned about the development of AI. Does anybody know what the picture on the right is the depiction of? Yeah, space elevator. And so this one's a little bit more far-fetched, but it would be a really big revelation in terms of getting things up to orbit. The idea of a space elevator is literally you just have a tether that's attached to the ground all the way up into space with a space station that's up at the level of geosynchronous orbit so that it just moves around the Earth. And basically the centrifugal force holds it in place, right? And so the only problem is obviously you need a really strong substance in order to be able to hold up against those forces, but things like carbon nanotubes have been suggested as possibly a way of doing that. But the nice thing is that at that point you're not using rockets to get things up into space. You're literally just pulling it up on an elevator system, a conveyor system, and it would be so much cheaper to get things up into space. So lots of different ideas that we went through tonight. Some criticism of sci-fi, but also some support of sci-fi. Like I mentioned, I'm a fan of sci-fi, and so I'm definitely a supporter, even if some of it goes a little crazy. I mentioned I'm a fan of Asimov, and so here's a kind of important quote that he gave at one point. Individual science fiction stories may seem as trivial as ever to the blender critics and philosophers of today, but the core of science fiction, its essence, has become crucial to our salvation if we are to be saved at all. And so one of the things that keeps me optimistic is that there's been so many things that past generations of humans have only been able to imagine, but then we've made true, right? And so I think it's a very important thing for humans to continue to do, to have those dreams, those imaginations, because in a lot of cases there really is the potential to make it true and hopefully make it towards a better world. Just real quick, I mentioned I'm going to plug the observatory before we take any questions here at the end. If you haven't been up to the observatory, it's over there, Mount Lookout, Hyde Park. It is the oldest public observatory in the United States. The telescope that's in the middle there is 180 years old, turns 180 this April, And it's a telescope that you can still put your eye to and use. It's the one that we use regularly for events. The one on the right is the Clark telescope. That's our baby telescope. It's only 120 years old by comparison. And so both of them are operational, and both are available to the public for a lot of different events. And speaking of events, we do have a lot coming up. There's always something happening up at the observatory for those that are interested in science. And especially we have adult activities, we have kids activities, we have family activities, and you can check it out all on our website. One of the things I've been doing is to offer classes, and so if you just have a side interest in astronomy and don't have the time to register for a full college course, this is just a way to kind of pick up a course here and there and learn a little bit more about the universe. There's talks about the history of the observatory, the history of the space race, and then occasionally we have large kind of festival scale events where we, for example, the next one coming up is Nearest Neighbors Night, where we'll talk about Venus, Mars, and the Moon, because they'll all be up in the night sky, and we'll talk about kind of future exploration, in particular about the Moon and Mars. So thank you all so much. I hope you enjoyed the talk, and I hope I get to see you again at the Cincinnati Observatory. Any questions from anybody? Mm-hmm.
Wouldn't some of that burn up as it went through the atmosphere? I know it's going fast because then you gravity acting on it,
Mm-hmm.
pull it down more. So how much of it do you think half of it would burn up? Some of it would burn up? What do you?
Good. So, yeah, the question was for the hypothetical impact where we had the 6-mile wide asteroid impacting the Earth. How much of that would burn up as it goes down through the atmosphere? It is true that for smaller objects, there's a significant amount that burns up, that vaporizes as it comes down through the atmosphere. Like, for example, the one that I mentioned that was visible over Cincinnati, that probably almost completely broke up and vaporized up in the atmosphere. And that's true for most small impactors. And small impactors could be something the size of a pebble or a marble, basketball, Volkswagen, like they said in the movie. Those are going to have a significant amount of burn up as they come down. When something is as big as 6 miles wide, the amount of time that it actually spends going down through the atmosphere is not enough for a significant amount of the material to vaporize. And so it's not a huge loss in mass at all for the really, really, really big objects. They're just so big, so massive that compared to the overall atmosphere, right? Like when you're flying in an airplane, for example, you're about 5 miles up, right? And here we're talking about an asteroid that's already 6 miles wide. And so the atmosphere is tiny in comparison to the asteroid itself, and there's just not that much time for the material to burn up. That's a good question, though. Mm-hmm. It's actually something that we see. For example, when we look at Venus's surface, which you have to use radar or in order to be able to see through the clouds, Venus, for example, doesn't have many small or medium-sized impact craters at all. And it's because it has a really thick atmosphere, all the small and medium-sized things get burnt up. It's only the large things that are able to get down and actually make an impact and crater. So the speeds are the same, whether it's a small object or a large object. It's just the fact that when you're comparing it to the overall size of the atmosphere, if it's big enough, the atmosphere just doesn't have enough time to really ablate the material. Yeah. Other questions? Yeah. Mm-hmm. Yeah, so the question was about Venus, and Venus being particularly bright in the sky. So Venus, there's a couple of cool things that it does. If you're looking for Venus right now in the night sky, all you have to do is go out after sunset and look over in the western sky, and it will be the obnoxiously bright thing over there. And while I'm mentioning it, if you can spot Venus, Saturn is just up and to the left of Venus a little bit. Jupiter is roughly directly overhead shortly after sunset right now and decently bright. And then Mars is over in the eastern sky rising. It's actually a really good time to look at the planets right now. But Venus, the question was about Venus being particularly bright, and there's a couple of different things that come into play, and they almost kind of compete with each other. One, Venus goes through phases, just like the moon goes through phases. And that's because it's interior to us here on Earth. And so when it's on the far side of the sun, that's when it would be at the full phase, but that also means that it's going to be really close to the sun and hard to see, right? And so when Venus is at the full phase, it's on the opposite side of the sun, further away, and it's really close to the sun, making it hard to see. Right? When it's in its orbit as it comes around, it'll start to go through kind of more than half full, which is called the gibbous phase, and then eventually it'll get around to like a half illuminated phase. And even though it's only half illuminated, that's kind of the ideal phase because it's far away from the sun, making it easier to spot in the night sky, early morning or late or early evening, and it's closer to the Earth at that point, right? And you might think, well, doesn't it get better as Venus gets closer and on the same side of the Earth as same side of the sun as the Earth? But the problem there is that when it's really close to the Earth, that means that you're seeing mostly the dark side of Venus, right? The illuminated side is on the other. And so Venus might be a thin crescent. Even though it's closer, it's a thin crescent, and so that takes the brightness back down. And so there's all those competing factors. It's actually a lot more complicated than you would think, but usually the best time is kind of when it's farthest away from the sun and how it appears in the sky. That help? Yep, that is what we're pretty close to right now. Yeah, we were actually, we had a Cub Scout group at the observatory back on Monday. It was extremely cold, but wanted to be able to show them all the different planets. And when we took a look at Venus, it's almost exactly at the half illuminated phase right now. Other questions? And yeah, it doesn't necessarily have to be about science fiction versus science fact. One of the things I'd love to do is just take like lots of random questions about astronomy too, if you have those. Yeah.
Have you seen any examples of science fiction that depict rovers either accurately or inaccurately?
So rovers? Yeah, so the question was science fiction that depicts rovers either accurately or inaccurately. One of the things that I should probably add to this talk, if I do it again in the future, is The Martian. Have you all seen The Martian or read The Martian? Matt Damon is in that. Well, Matt Damon is almost exclusively in that movie because he's trapped on Mars. Spoiler alert, sorry. But that is actually a really good depiction of how a future Mars mission might go. And in that, he actually goes and retrieves one of the rovers and actually uses it as a form of communication, kind of a backup communication with the Earth. So that's one thing that I can kind of think of in terms of accurate depiction of a rover. In general, the author for that book did a lot of really good research on what future Mars missions might be. There's really only two things in that movie that are a little bit off. One is that they don't bother to show the weaker gravity on Mars. So throughout the movie, the astronauts and Matt Damon are moving kind of, just like they normally would on Earth, because it would have taken a lot of extra special effects in order to show the fact that they are lighter. They could jump higher. Even just walking would probably be slightly different. And then the other one, I don't know, do you want me to spoil things or no? Am I okay? All right. So the whole premise of the book and the movie is that he gets trapped on Mars, and it happens because a very severe dust storm happens on the Martian surface, and they have to rapidly evacuate. So, one, dust storms absolutely do happen on Mars, and they can be quite intense. There's actually even occasionally dust storms that completely envelop the entire planet. But in the movie and in the book, he gets trapped because the winds are so strong during that dust storm that he actually, I think, ends up getting impaled by a piece of equipment that is blown over and then blown into him. And the author even admitted that he used this as a plot device. The problem is that Mars's atmosphere is very, very, very thin, right? It's 1/150th the thickness of Earth's atmosphere. And so there is wind on Mars. It can pick up dust. But the wind is made up of air that is 150 times thinner than what's here on Earth. And so you could stand in 100-mile-per-hour winds on Mars, and you wouldn't be blown over because it just doesn't have that much force behind it. There's not that much material behind it. It can pick up dust, no problem, but it's not going to blow over a human or a large piece of equipment, and it's definitely not going to blow it over with force enough to like impale somebody. And so those are two tiny little nitpicky things in what is otherwise a really, really, really good book and a really, really good movie. That was probably more than you wanted besides the rovers, but sorry. Yeah. Other questions?
Do you have an approximation of, because obviously Mars is between the moon and Earth, as far as gravity goes, do you have an approximation of what walking or things would look like?
Yeah, the question was, do I have like an approximation of what walking or anything like that would be like on the Mars's surface, because it's basically in between the Earth and the Moon's surface. I don't. I mean, maybe if you have, I have a few more beers, I can do an impression of what it might be. But this is kind of related. You might have heard of. There's a NASA airplane, and also there's some private companies that do this as well. They're plane flights that are referred to as a vomit comet. Have you ever heard of those? They're called a vomit comet because obviously it can be very disruptive in order to go on these plane flights. But the whole idea is that it's a plane flight that goes through these crests and troughs. And so the plane basically climbs to a certain altitude and then dives, and then climbs back out of that and then dives. And when it's at the top of its crest, think about being on a roller coaster, if you've been on a roller coaster, or even think about being on like a hilly country road and you go over a small little hill and you feel that sensation in your belly. That sensation in your belly is because for a moment at the top of that crest, your organs are kind of weightless with respect to your body. They're floating inside your body. They do this with the planes to simulate what that floating environment is like. And if they do one type of trajectory, they can actually have people floating in the cabin, right? They're literally floating around. There's awesome videos that you can watch of those people doing it. But if you do a slightly different trajectory, you can simulate Mars gravity. And if you do a slightly different trajectory, you can simulate the moon's gravity. And they actually intentionally do Mars gravity simulations where they test out the suits that they would like the Martians, they would like the astronauts to use when they get to Mars, just to test out how easily maneuverable they are in those kind of conditions. Because that's the only way that we have to simulate those conditions. And it only happens for maybe like 20, 30 seconds at a time as it goes through those bounces, as it goes through those trajectories. But it's 20 or 30 seconds of data that you otherwise wouldn't have. Yeah. Other questions? Would you all go on a vomit comet? Like I said, there's actually private companies that sell like tickets for a few $1,000s or something like that to take you out there. It looks like it would be fun, but I already kind of am scared of flying. I don't think I could do the dives over and over and over again. Good. All right. Thank you all so much again.
Thank you so much for joining us tonight. Thank you. Be sure to check out the observatory. Science on Tap is generally the first Wednesday of the month. Sometimes we change it, like this month. Follow us on Meetup or on Facebook. All our previous events are on Radio Artifacts YouTube channel if you want to go check out some of the previous events. And I hope to see you at an event soon. Thank you all for coming.
I made a brand new friend today. She smokes all of my cigarettes. She's gone left me in a haze, with folded arms across my chest, and I'll keep lying on the floor, hoping you're